Is my clicker working? Fantastic. So, for tuning queries for performance has many aspects to it, right? Mainly indexes, tuning the queries, but there are other aspects as well in terms of, these are the topics I'm going to cover in today's talk. Data model, the query execution model itself, and the indexing options that you have, the design of the indexes, and then finally query tuning and a couple of comments on deployment and configuration. Right? Yes, we want the best performance. The best performance starts with a right data model. Right? Once you have the entity relationship logical model, you have to represent that model within Couchbase. Yes, Couchbase with its JSON model has flexible schema, but you still need to start with a schema that evolves dynamically, right? So that means you are defining the boundaries of each documents, identifying the parents and child objects, and deciding whether to embed the child objects in the parent object or represent them as distinct objects, and defining the relationships. These relationships can be parent-child relationships or independent relationships that you query independently as well. So expressing these relationships in the right object is the first step to realizing your logical model into a physical model. In Couchbase, parent and the child object, if they are represented as separate object, as separate documents, they have their independent life cycle. That's a indirect way of saying we don't have cascade deletes. Right? If you have two different objects dependent on each other, you will if the parent goes away and you want the child objects to go away, you have to delete them independently. And having the object child object embedded in the parent object or representing them in separate documents has performance implications. We'll discuss that. In terms of atomicity, or when people who are coming from SQL world, Couchbase has per document atomicity. That means if you are updating multiple documents with a single update or deleting multiple objects with a single delete, we don't have the transaction semantics around a statement, around set of statements. So if in the middle of the statement, if the statement gets aborted, we don't roll back all of the updates that was done by the statement. You will have to have that check and corrective action as part of your application logic. Embedded child, that means a bigger document size, makes it easy to get all the object and its related information together. That means you don't need to join in the backend. When you get a customer object, you get customer and its related objects with a one single fetch, whereas if you represent customer and their connections or connection information or billing information as separate different objects, you need to do the join before you get back. So that's the trade-off you'll have to decide as you realize your logical model into the physical model. We talked about the parent child relationships already. So how you represent the parent-child relationship has a big impact on the performance. The three ways to represent these relationships in Couchbase: parent, if it doesn't already embed the child within the object, can have a pointer. That means it can contain the keys, document keys of its children. So for you to represent relationships within Couchbase, it's best to have one object containing the document key of the other object, because the joins in Couchbase are done through the document keys. So one document having the document keys of the other document makes it easy to join. On the flip side, the children can have the keys of the parent or parents, so you can join either from parent to child or child to parent within the query language. You can do either, or you can do both within a single model as well. So on the left hand side, you see a customer object represented with 5 different relations or relational tables. So in relational tables, you can model a complex object and normalize the data into multiple relations that are represented as multiple tables. That's perfectly fine. That means every time you persist, you're disassembling the object into multiple tables, writing them, and when you want to get the customer object, you're getting the data by joining all these relations and constructing the object dynamically. In different talk, we went through this evolution of how a customer object can be, from a 5-table representation, can be transformed into a single JSON object. In here, you can see the billing information that's represented by multiple rows in a relational table can become multiple objects within a single array in the billing attribute. Similar thing with connections. Multiple connections represented as different rows of a connections table are saved as multiple objects within the collections array. So JSON gives you all this, apart from the flat key value pair, it gives you object and arrays of objects, arrays of objects. So you can have a complex model represented with Couchbase in a single database. Yes, complexity or more nested object is good, but it's no good if you can't query it efficiently, right? Eventually, you want to create the model so that your application developers, your tools can get to the right data. As Kyle showed, they have to be able to get to the data in milliseconds and seconds, and I'm going to focus on that for the rest of the talk. Kyle alluded to this earlier. Our travel sample has got 5 different tables of 5 different logical key spaces, all stored in the same bucket. We use the type. You can use any of the key names as the discriminating field. We are using the type to discriminate or to differentiate between the different document types. So let's look at a sample document. I've taken a hotel document that represents many relationships within a single document. In this case, hotel, for example, hotel is in one city, so there's a one-to-one relationship there. So that is stored as a simple key value store. Same thing with the geo object. So, city was a simple key value attribute. Geo is an object. You can have an object in there representing a complex information within the hotel, and because each hotel has only one geo information, it's a simple object containing its accuracy level and lat long. It's a one-to-one relationship. The public likes, however, is one-to-many relationship. So there could be multiple people who have liked this hotel. So you model this as a attribute, as an array attribute containing multiple scalar values, right? We just are storing the names of the people who have liked it. So those are all simple scalar values. Reviews, on the other hand, can be quite complex. You have the author name, you have the content of the comments, the date of the reviews, as well as rating of the hotel based on multiple criteria. So how was the check-in desk, how was your cleanliness, and so forth. That becomes an object itself. So reviews become arrays of object itself. That represents one-to-one relationship, and each of the arrays store not just scalar values but a complex object. So this shows you the power of modeling your data on JSON. Now we'll talk about the power of query processing on top of it. Okay. So in terms of actual access methods for each of the Couchbase documents, the use keys modifier to the key space, that means you already know which documents you need to get to. If you use key value API, if you know the document key, you can fetch the document. The same access method is provided in Nickel as well. If you know the keys, use the use keys and there is no index used, we go ahead and get the data directly from the key value store. That's the fastest. If you have to do any complex query processing, a covered index scan, that means the complete data required by your query is saved in index. Index already has ordered the data. Index can filter the data. That means you don't know what document keys that you're interested in, but you want to get subset of the data. You're doing set processing. So a covered index scan is the best, because we just need to do index scan to answer your query. Regular index scan is index can do the predicate processing. That means index can do the filtering of the data based on your predicate, but it doesn't have all of the data that you're trying to project. So then we use the index for filtering data, filtering the documents you're interested in. We get the qualified list of documents. We go ahead, fetch the document from the key value store, and then do the rest of the filtering, aggregation, and projection. And then joins, of course, have to deal with multiple key spaces. Joins are slower as well. Last probably the least used, or this is the method that should be used the least. That's the primary scan that scans the complete bucket to look for the data that will answer your query, right? So one of the tips is, it's okay to have primary indices and queries use primary scan when you're doing development, when you're doing experimentation with your queries. But in production, if somebody is doing primary scan, you probably have the wrong plan, or you don't have the right index, you don't have the right predicate, and so forth. So in terms of modeling, how does the modeling map to the access methods you're using? If you have embedded the child object into the parent object, that means you have all the information that you need in a single object, and you can use the use keys to get the object that you need. If you have outbound relationship, that means you are representing parent and the child in multiple object types. You do the joins to get the documents that you need. By the way, just because these are different access methods doesn't mean that each query has to use only one of them, right? You can use index keys and joins. If you have a customer object and you want to join with orders, you want to join with sales and returns, you can do all these combinations in a single query. That means your real world model is complex. You have many types of objects, many types of relationships. That's the reason we added, even though we are a NoSQL query processing on a NoSQL system, we have had the select, join, nest, unnest project operations from the first release, so that you can represent your complex real world model with Couchbase and do the query processing using Nickel. So then moving on, the inbound relationships where the child has the pointer to the parent can do index scan as well as the index join. And when you don't model any relationship, you end up using a primary scan. That's the access method of the last resort. Okay, so with that, for those who haven't tried out Nickel yet, what Nickel does is it takes sets of JSON documents as inputs, does the query processing based on your query, and gets you back the set of JSON document. It's true for select, it's true for insert, it's true for update, right? Logically, delete takes sets of documents you have, given the predicate, it deletes set of documents, and the result is the remaining documents. So all the operations operate on JSON and give you the JSON back. In terms of actual execution, your applications either using our SDKs or ODBC, JDBC drivers or REST API directly submit the queries. Query service does the parsing analysis and creates the plan. If you're using the index, we go ahead and do an index scan, push down the filters, get the qualified keys. And if you're using, if we require to access the data to answer your query, we go ahead and fetch the data, do the further filtering, joins, aggregations, sort, and pagination before we return the results to the client. And this is the kind of the gory details of how the actual execution happened with different phases. Just one thing to note is, when you see a single phase with a single block, that means this phase is executed serially, like the parsing and the planning is executed serially, whereas scans, fetch, joins, filter, these can happen in parallel. Fetch, when we have to fetch the data from the KV store, we always fetch the data in parallel no matter what the setting is. For other phases like the scans, the joins and filter, there's a parameter that you can set on a per query basis, or you can set on the whole query service called max parallelism. By default, it is set to 1. If you want to increase the parallelism, you can set per query or per service as well. Okay, with that, let's look at all the different indexing options you have with Couchbase, right? So there are many ways to create the index. We have actually written detailed articles in dzone on with usable examples for each one of them. So this is probably the probably a very important slide. I'll go through each one of them so you get an idea of what they are. Primary index scan. This is the equivalent of your full table scan in relational systems, right? Primary index creates an index on your document key, and primary index only has the entry for document key in a sorted order, and it has a one-to-one relationship between the index entry and the primary index. This is the index used if there are no other indices qualified for your query. That means your query has predicates that doesn't qualify for any other index, or your query doesn't have any predicate at all. Named primary index. So if you do use primary index, you won't have high availability for your primary index. So you can have multiple primary indices and name them differently, so you get high availability as well as scalability. If there are queries that are using primary indices, we do the load distribution among these indices. Secondary indices. So any indices on any of the key value attributes within your document is a secondary index. You can create indices on pretty much any field, whether they are on the top level or whether they're stored in the objects within the document. So they are all secondary keys. So a simple secondary key is on one key, and a secondary composite key is on multiple keys. Just like a composite key in relational systems, you can have indices on multiple keys. They are called composite keys. Functional keys, the common use case for this is, you have names, but you want to search the names in a case insensitive manner. So you create an index with a upper or a lower value, and whenever you want to search for a index, you have the predicates with upper of the value compared to the upper of the actual key name. So you can index not just on the value, but a manipulated value of the actual key. So that's the functional index. Functional index, we support not just functions, but also arithmetic expressions and so forth. So you can do very interesting stuff. One of the most powerful things you can do with JSON is the ability to have arrays, right? Yes, objects are there. Object gives you nesting level. That gives you some flexibility, but having arrays means you can have arrays of scalar values, arrays of objects. And as important as the modeling is, it's even more important to have the right access method to get to the data, do the filtering based on the data. For example, if you have a customer with many orders, you want to be able to filter the data based on a order greater than a particular value. or if you have a customer with many billing information, you want to be able to look up the data based on a particular type. So array indexing with Couchbase gives you the ability to index a particular element within an object of an array, no matter how deep the nested is. It can be, you can have arrays of objects, you can have arrays of objects of arrays. You can index a particular value within Couchbase. So that means the index is very efficient and you can get to the data very efficiently. Partial index. As I mentioned earlier, partial index, okay, let me step back a little bit. In Couchbase, you use a single bucket to store multiple types of documents. You saw the hotels, airlines, and all that. We use a type field as a discriminating field to differentiate between the different documents. That means when you create an index on a field in the hotel, you just want the index to contain data within the hotel. So you can have an index where type equals hotel. That means this index is just for hotels only. Other index for airlines, other index for routes and so forth. So this partial index gives you, in its simplest form, partial index helps you to index on individual groups of documents. The other way I look at it is, this is a kind of a poor man's way of doing partitioning within Couchbase. How many of you used partitioning features in Oracle or SQL Server and so forth? Okay, good percentage of you. So you have range, for example, range partitioning in SQL Server and Oracle. You can implement the same similar thing with partial indexes, except when you have queries that go across the different partitions. We don't exploit the indices yet, right? So that's one limitation you have, but you still have ability to index on subset of the data. Finally, covering index. Covering index is not a special type of index, but it's an attribute of an index where you have designed the index to cover n number of queries. That means those queries can be answered just by looking up the index. So we call them as covering indices, and queries are covered queries. Duplicate indices. We call two indices as duplicate indices when two indices are identical except in their names. Their keys are exactly same, their conditions are exactly same, they are indexing the same bucket, only the names are different. We automatically identify two or more indices to be identical, and during query prepare phase, we choose one of the indices to create the plan, but at runtime we know which of the indices are identical, and we do the load balancing across them automatically for you, right? So there are many different ways to create the indices. So if you understand the different type of options you have, you can study the indexes and create the right queries and indexes and create the right indices for you. So creating the right index is a very, very important phase to get the best performance for your queries, right? So let's take a look at the query here. Take a look at the document here. We have an airline document which has few key value pairs. So this is not so different from a simple relational row. So now this document has is of type airline, right? And then the goal of our exercise is to get the lowest IDs that are the lowest 6 to 15. That means we want to offset 5, get the next 10 IDs between 0 to 1000 of the type airlines, and we want the country to be United States, and we want to project country, name, value, and IDs. So let's see how we can write the queries for this, right? So our query to answer that problem is select country, ID, name from travel sample, and we have represented the requirement as the in the where predicate, type is airline, country is United States, and the ID between 0 and 1000. And we want the results by ID, and we are interested in only 10 documents, but we want to ignore the 5 documents that we get, right? When you have results of your search or results of a query in your application, when people navigate from first page to second page, the pagination with a given order is a very common use case. If you have only one index for this, if you only have the primary index for this, we have to fetch about 31,000 documents to do the query processing. We fetch all the documents, apply the predicates, do the sorting, and do the pagination from there on. So then we need to, we say, okay, this is too much. I get the answers in a few seconds, so it's too slow. I want to improve the performance. Let's say you look at this query and say, I'm going to create the index on the type. I have airline as a differentiating field. I create the index on it. Well, once you create the index on type, we can only push the type equals airline predicate into this index. So we have about 187 documents of type airline. So that reduces the number of documents we fetch dramatically, right, from 31,000 to 187. But even after that, we are still fetching 187 documents, but eventually the application is only interested in 10 documents. So we're still doing extra processing, right? One of the lessons I learned early on when I started with the database systems is, best optimizer technique is the one that does no work at all, right? You still get the same result, but you want to do the approach to optimization is to see how much work we are doing and try to eliminate the work as much as possible. So eventually you want to do as less work as possible, but still return the accurate result, right? That's still is the number one requirement. Well, we have improved this, but we still have an opportunity to improve the performance. Now we say, okay, let's create a composite index with type, ID, and country that covers all the predicate. That's fantastic. So we can push all the predicates and get the required documents, and we fetch about 18 documents, right? 18 documents qualify for a predicate, and that again reduced by 1 order of magnitude from 187 to 18. Now we said, well, we had the type as a differentiating field, and why not we make it a condition, right? We are already grouping the documents by airline, hotels, and all that, and we create an index with ID and country and move the airline to the as a condition to the index. One of the things that happens when you move a key to the condition is the keys in the condition do not get indexed. That means the index becomes linear. We go back to having just two keys, but you still get very good filtering from the index. Next thing is, well, we have all these predicates, but you know what? Apart from these predicates, if you see the query, we want to project the name as well. Right? We want to project the name as well. So we go ahead, we want to make it covered. We just don't want to get the data at all. So we go ahead and add name into the index, so the query is completely covered. And now with this, we get both the predicates pushed to the index, but our order by is on ID, right? If you have the leading key of the leading keys of the index match the order by clause, that means leading keys of the index follow the same path as the order by, we can avoid the since the data is already in order in a pre-sorted way in the index, we can avoid the order by itself, right? For us to exploit the index order, the index key list has to match the order by list. We should be able to push down all of the predicates to the index. So then we can exploit the index order. So we eliminate the order by itself. Last but not the least is when we have the offset and limit, we can if we are having if all of the predicates are evaluated by the index, we can push down the limit processing to the indexer as well. So that way we don't need to fetch more data than required, right? So indexer will return only the limited number of documents. So we get the results back to you. Okay. So in this case, in this case, when we want the results by country and ID, here the order by list, that is country and ID, matches the country and ID in the index, and we can exploit the index order. And in 4.6, which was just announced as beta today, we do some further optimization even when you don't have the order by on the leading keys. If the leading keys have equality predicate, we know the results is going to be logically not just logically and physically exactly same. So we do further optimization even when the order by clause doesn't match the index key order perfectly. Okay, so for the query we started, here is the final suggestion on the optimal index creation. If you have a query with these three predicates, you can create an index with this. You require these three keys, country, ID, and name, so that it completely covers it, as well as the where clause with type equals airline, so that this index is chosen to cover the complete predicate as well as the projection list. And because it matches the order by clause, we can exploit the index ordering and push down the limit and offset to the index scan as well. Okay, so now I won't go through the couple of other examples in the interest of time. So because you have functional indexes, I mentioned earlier, apart from upper and lower, you can have expressions like this. So you can index the values either by ascending and descending order, but you do have to write the query to match the expression within the index. So you can have the flexibility in terms of ascending and descending within the query. Okay. Now index design. So you saw examples of you saw the variations of different indexes that you can create. You also saw the examples in our query walkthrough. So here is the advice on how to go ahead and design your indexes. We have two types of indexes in Couchbase 4.5. The standard GSI indexes, which support smaller mutations, and but it can have very large indexes, because if the index is larger than what it can hold in its buffer, it has persistent memory, persistent disk. It persists the index on the disk. Our memory optimized index is optimized. The data structures are optimized to keep the whole data in memory. So it supports tens of thousands of mutations per second. You saw in the keynote the memory optimized index that Perry showed was supporting 500,000 mutations per second. Some incredible performance, but all of the index has to be in memory. Avoid primary index scan in production at any cost. I would say you can't avoid tables. You can't disable table scans in many of the database systems. But here, if you don't have primary indexes, you are saving yourself a lot of headache. Query has to have the right predicate to choose the index. right? So the explain plan will show you whether we are choosing the index or not. Query needs to have the predicates and the leading keys, right? Other keys can cover the query, but leading keys are important. You saw there are 9 different types of indexes that we have. So explore all the different options in terms of partial indexes, the index key order before you settle down on an index. And with functional indexes, we support complex expressions both in the keys and even the partial indexes. I showed the simple type equals airline. You can have type equals airline and ID between 0 to 1000. You can have complex expressions both in index keys as well as the where clause of the index, so you should explore that as well. Index keys can have large number of keys. For operational queries, you want as low latency as possible. So you can have very wide index. By default, our max index key size is 4096 bytes. So yeah, you should treat the index keys with predicate attributes as the leading keys, followed by non-predicate attributes for covering. That means whatever keys you are using in the filters should come first, and whatever your keys you are just using projection, like the name example you saw earlier, they should come towards the end. When you create the index, typically you should have whatever keys that you have with equality predicate are in predicates. In predicate is a different way of saying equality predicates. They should come first, followed by less than or less than equal to or greater than equal to, and then followed by predicates which use just less than, followed by predicates that use just greater than. If the partial index condition has equal predicate on the field, you don't need to include them in the index keys. In the example earlier, we had type equals airline. Even if you project the type in your query, we know this index contains only the airline. We can even project that value with our query. You can look at the console to see what indexes are being used, what indexes are unused. So try to drop unused indexes, because unused indexes takes resources from your systems. Yeah, okay. So yes, indexes, memory optimized indexes has to stay in memory completely. But if you run out of memory, if you want to scale out, you can create partial indexes. So you can subdivide the indexes into multiple indexes and then scale out. Okay. In terms of tuning query performance, the moment you see the query is not performing well, first thing to do is to explain. So you get the explain plan and try to understand what is going on in the life of the query. What indexes are being chosen? Are we pushing the right predicates into the right index? Do we have the right index selection? Sitaram, lead engineer in query development with Couchbase, has written a very detailed 30-page article that's available on dzone.com. You can go ahead and look at how the index is used, how the predicates are pushed down in each of the combination of values. There are 30 use cases that we have written, so you can try that out and be comfortable with it. And then limit and offset are and you have to check if the limits and offset are pushed down to the index scan, as well as the index order. Does the index order match with the query order? As much as possible, you should try to have index design so that it covers the queries, but it's perfectly fine if we are getting a few documents post index scan as well. Simple count queries or simple count aggregates are pushed down to the index scan. So and same thing with min aggregate as well. If you're using array indexes, what we support is any predicate, any and every, and within predicates. So make sure that you get the explain, and we are pushing down the predicates on your arrays to the array index. With unnest, the array index key has to be the leading key, and there's a tendency for people to use, even when you know the exact attribute within the object, it's a tendency to use within instead of in. The in predicate within the array index is much more efficient than the within. With 451, you have the option to turn off predi equals false, so that the result set is more efficient. I'm getting the sign, so these slides will be up on our website. Take a look at some of the tricks and tips additional tips we have in terms of the query processing. I have some usable examples for you as well. This is the last slide. So query processing has some default values in terms of how many documents it fetches. So you can change the config. If you are doing query processing with very large amounts of data, you can change the values per query node, or if you use our DAG eval, you can change the values for the whole service itself, right? Okay, that's the last slide. So I'm happy to hang around to answer any questions. Thank you.